Hello and welcome to Chem 3, the Chemistry Formulas 3 program from MCS Tutoring, a TI-84 plus calculator program. Okay, just so you know, we do have solver programs for chemistry. We've got two solver programs that will solve pretty much everything you see here. This is only a formula program, so if you just need help and see the formulas, like say for molarity, let me give you an example here. So this is what this program does. It shows you, hey, this is the formula, molarity equals moles per liter. And here's an example. We've got 0.5 moles. We've got 2 liters. This is how you calculate the molarity and gives you the solution to the sample program or sample problem with numbers. So if you're looking for solving a program, we have ChemSolve. I think there are 2 variations. One is for first semester chemistry and another is for second semester chemistry. And again, for intro chemistry class. This is not organic chemistry, guys. So we go on. So let me just show you an example. We showed you the example of molarity for stoichiometry. Let's do percent composition. And look, this is one of the cool aspects of this program. It will solve for different things. So you have percent composition. You're not always looking for percent composition. Sometimes looking for mass of an element or the total mass. Let's do percent composition. So percent composition is mass of element divided by total mass times 100. So let's see with the actual numbers. So here's an example. Mass of elements 3 grams. The total mass is 18 grams. So percent composition will be 3 divided by 18 times 100. So percent composition, 16.67%. So this is how most of this program works. There are some examples where it's just giving you the general format. I think for the gas laws, I'll go there presently. So for the gas laws, it doesn't solve all the time for every single variable. There are just too many gas laws here. So to keep the program in one program rather than splitting up into 2, it just gives you, say, an example, excuse me, ideal gas law, PV equals nRT. Gives an example, gives you the N, the R, the T, and then the volume. And solving for P, blah, 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 it works it out. Okay, sorry, I didn't open that parentheses, but you get the gist. Okay, so, and then let's do Charles' law, for example. V1 equals V2 times T1 divided by T2. Here's your example with the V2, T1, and T2 given. And then this is how you find volume 1. It's approximately 1 liter. So we go on. And then this is what I like. I did have a help menu. A student actually contacted me. I don't know if it's on YouTube or contacted me through my site, mcstutoring.com. They said, could you have a help menu for all of these? Because I don't know what I'm doing in chem. And I'm like, hey, that's a brilliant idea. So gas laws help, ideal gas law, PV equals nRT, and then use consistent units, atmosphere, liters, Kelvin, and then all these Boyles, Charles, etc. for combined gas law, ensure T is in Kelvin, select the proper R. Now that's what's funky. I do want to get to that. There are different R's. Okay, that's where people get tripped up. So I do want to go over that for the constants right now. So the gas constant, man, it depends on what your units are for the problem. So I was getting this constantly wrong in high school chemistry. So if you're doing liters, atmosphere, mole, Kelvin, you do 0.08206. That's liters times atmosphere divided by mole times Kelvin. If you're talking about joules, which I think is a work thing, 8.314 joules per mole Kelvin. If you're talking about like millimeters of mercury, 62. Gosh, English is my first language. 62.36 liters times millimeters of mercury per mole Kelvin. So I just wanted to mention that. That I don't know, that just bugs me, but I put that there for that reason. So for thermochemistry, we got enthalpy, heat capacity, temperature change, Hess's law, STP conditions, and help. Let's look at the help menu. So H equals Q plus W. Q is in joules, W is in joules. C sub P, I think that's, oh my gosh, I'm going to remember in a minute. It's joules per gram Kelvin. T is in Kelvin. Is it the specific, not specific heat, I'm forgetting it. Hess's law and STP are explained. Review your units. I put that there, not as a finger wag, but just so you guys know, that's where your mistakes are most likely made in this particular section. So let's go back to thermochemistry, and let's go to heat capacity. So the formulas, molar heat capacity, C sub M equals C times MM. Let's get an example here. So if C is 4, is that specific heat, I think? 4.18 joules per gram Kelvin. I think the molar mass in this case is 18 grams per mole. Suspiciously sounds like water here. C sub m is the 4.18 times 18 equals 75.24 joules per mole Kelvin. Okay, good. Let's go to the solutions here. So we've got solubility, colligative properties, molality, osmotic Van't Hoff, Clausius-Clapeyron. Forgive me if I'm butchering the name. And solutions help. I always need help with solutions. Let's do this. Solubility is moles per liter. Molality is moles per kilogram. If you guys would like me to sound more decaf, just type in the comments. I'm a micro YouTuber. I read all my comments. So if you'd rather I just go slower, that's cool. I can do that. Percentage, I think, is M over T times 100. We can do that. I'll just chill out from now on in this video. Boiling and freezing point, osmotic pressure. Pi, I think, is, even though I know you guys think it's 3.14, I think for this specific application, it's P is for pressure or pi is for pressure. I times M times R times T. I is the Van't Hoff factor. M is molarity. Again, moles per liter. I was confused a lot when I was your age. I thought it was like molality sometimes, which is a separate thing. R is 0.08206 liters times atmosphere per mole Kelvin. T is in Kelvin. Pressure, Clausius-Clapeyron. It's the natural log of P2 over P1 equals negative HVAP. I think that's heat of vaporization divided by R times, okay, and this is one big old thing, 1 over T2 minus 1 over T1. And again, I have examples, so don't fret yet. HVAP is in joules per mole, temperatures in Kelvin. R is 8.314 joules per mole Kelvin. So what was that? Was that solution stuff? Yeah, let's just do Clausius-Clapeyron. That just sounds gnarly. ln P2 over P1 equals negative HVAP divided by R times 1 divided by T2 minus 1 over T1, where HVAP is enthalpy of vaporization. Oh, I was wrong. Joules per mole. Okay. R is 8.314. T is in Kelvin. And then here's an example. P1 is 1 atm. T1 is 350 Kelvin. P2 is 0.5 atm. T2 is 370 Kelvin. So this is kind of giving you what's going on. It's ln of 0.5 divided by 1 equals negative 0.693. 1 over T1 minus 1 over T2. That's 1 over 370 minus 1 over 350. And then, which is approximately 0.000154. So you plug it all in, and these are the numbers it spits out. So it's pretty cool. If you need to rerun it, you can just, take notes. So you see how to work an actual example. And this is for students who really just want to kind of see their way and are probably good at math. If math is your Achilles heel in chemistry, definitely go for the Chem Solver programs available at mcstutoring.com. You can check, probably link in the comments. Like I said, let's go into acids and bases. Got to move on here. We got pH, pOH, Ka, and Kb, water constant, acids and bases help. Let's go to help. pH is negative log of the hydronium ion, and pOH is negative log of hydroxide ion. If you add the pH and pOH, you get 14 at 25 degrees Celsius, or centigrade if you're fancy. Use proper units for concentration. Ka and Kb equations help with weak acids and bases. I'm assuming that's implying something different for strong acids and bases. So let's go back to acids and bases. Hey, let's do pH and pOH. So you can solve for pH, pOH. You can get hydronium ion concentration from pH, hydroxide ion concentration from pOH. Let's just do pH standard. Write negative log of this. So if the hydronium ion concentration is 1 times 10 to the negative 7 m, pH should be negative log of that number, which would give you 7. So it's pretty cool, giving you examples, as I said. Let's go electrochemistry. What is going on here? Sorry, electrochemistry 6. Nernst equation, Faraday's laws, example of Nernst, example of Faraday, electrohelp. Let's go electrohelp. Nernst equation is this. I don't even know what these units are anymore. I'm so lost. I'm more of a math guy. But I will go to electrochemistry. Wait, I can't go to negative. I'll go to 6. Let's do actually a Nernst equation thing. So you can solve for the different ones. As I said, that's the majority of these subsections. You're going to solve for a specific variable, which is cool because, you think, oh, you just got the formula, you're good. No, sometimes it's tricky and you're solving for E or E with this degree symbol or T or N or F or ln of Q. So without further ado, here's the numbers. I know you can make it out. So E is approximately 1.10. I don't even know what V is at this point. I'm losing it. So let's go to, I think we did everything. I'm not sure, maybe. Let's go to kinetics. Let's get rate law, Arrhenius 1 temp, Arrhenius 2 temp, reaction half-life. I don't even know intermediate rate law. What is that? Oh, yeah. Okay. So you got 0 order, 1st order, and 2nd order. Man, a student, Johnny Utah, shout out to you, dude. You contacted me via the site. You're like, hey, man, can your program do this? I'm like, not yet, but give me a week and it can. And now it can. Ha, ha, ha. So shout out to Johnny Utah for this. He's more in the chem solve programs because math isn't his strong point. So 0th, I don't even know if that's a thing. 0th, whatever, order reaction. AT equals A0 minus K times T. T sub 1/2 is A0 divided by 2K. What does that mean? Okay, so an example. Let's say your A0 is 0.8 m. K is 0.02 m per second, I'm assuming. T 1/2 is 0.80. That's the A sub 0 divided by 2K. So it's 2 times this K value, the 0.02. And there we go. So that's kind of cool. I do like that, even though if I don't know what chemistry is, I feel like it's the Searle's Chinese language room argument, and I'm in the Chinese language room. I'm the homunculus. Okay, let's go to equilibrium. Why not? So we got the equilibrium constant, Le Chatelier's principle, reaction quotient. I know you know how to read, so you can just press pause and read. Equilibrium help. Let's see what help is. Okay, so I do have this. I know some students, in fact, Johnny Utah is like, hey, man, what if we have like A yields B plus C, or A plus B yields C, or A plus B yields C plus D? So I don't have every single variation accounted for, but I have enough to get you started. So let's go on with that. Was that the more? Yeah, equilibrium. Okay, let's actually do one. Equilibrium constant. So we've got Kc equals C raised to C, probably D raised to something, whatever. Let's solve for K sub C. So, here's the actual equation in its entirety. C raised to the C, D raised to D, divided by A raised to A, B raised to B. So we've got nitrogen plus 3H2 yields 2NH3. So yeah, this is what it looks like, guys. Boom, boom, boom. Okay, great. I don't want to comment on it because I don't understand it. Let's go to nuclear reactions or nuclear chemistry, half-life, types of decay, example of half-life, decay equation, activity, mass, energy, and nuclear help. If you do comment like, hey, I want to see this program in its entirety, I want to see all the screens, comment it, and I will make such a video. So unless and until I see that, I'm not going to do that because that's going to take a long time. And I will just be quiet most of the time during that video because, like I said, I don't really understand a lot of the chem. I just know how to make it look nice. So T sub 1/2 equals ln2 divided by lambda. I do know a little bit of Greek. Lambda is 0.6. So if this is given, 0.693 over T1 or T half-life, I think, and your time of half-life is 5,730 years for like carbon-14. T half-life is approximately 5,730. Okay, yeah, 0.693 divided by that. Okay, whatever, something like that. And then let's go to the more menu again. Was that nuclear? Yeah, let's go to redox reactions. I kind of get this. Oxidation reduction. Half reactions, let's do that. Why not? So oxidation is loss of electrons. Reduction is gain of electrons. It's counterintuitive that way, but it means reduction means you're reducing the charge. So you're going more negative. So Zn plus Cu2, I think that's like copper 2 plus, yields Zn2 plus Cu. And this the oxidation is this half reaction. reduction is this half reaction, and the overall is this reaction. So it's kind of cool. It breaks it down for you, so you see what's going on. Let's go to the constants. So you got the gas constant, avocado. I eat a lot of avocados. That's why I'm confused here. Avogadro's number, Faraday constant, Planck's constant, and Boltzmann constant. I don't even know what that is. Let's look at it. It's 1.381 times 10 to the negative 23rd joules per Kelvin, or 8.617 times 10 to the negative 5th EV per Kelvin. Okay, good. Now I learned something, maybe. So let's go to the more. Unit converter. Okay, this is the part of this program where actually something is done. I actually convert common units for volume, temperature, time, mass, and pressure, or just SI units. So first, and this is kind of cool. I think so. Select your starting prefix. So let's say we've got mega, like we're going mega liters to liters, okay? So we're starting with megaliters. We're just trying to get to liters, which is unit. I put it here so you're kind of like, oh, this like sticks out a little bit. We're going to go to the unit, okay? And then how many? Let's say we have 8.3 megaliters. How many liters is that? A whole bunch. Looks like 8.3 million. Should be a comma here and a comma here. I don't know how to code that yet, so I'm not coding it, but there's the number you want. Okay, great. So that's basically it. Pressure, you can go ATMs to pascals, pascals to ATMs, ATMs to, or atmospheres to millimeters mercury, millimeters mercury to atmospheres. Let's go millimeters mercury to atmosphere. Let's do 780. Ooh, it's 1.02 ATM. Well, it's 0.026. Okay, so look, there it is, pretty much just a brief introduction, maybe not that brief, of the chemistry program from mcstudium.com. If you like it, like it. If you don't like it, don't like it. That's cool. If you want to see more stuff like this, subscribe. Comment if you have questions, stuff to add. Excuse me. I'm losing my voice here. And then the other thing is, if there's stuff you want to see, seriously, put it in the comments and I will make it, because this is not the first or second iteration. This is the third iteration of chemistry formula program. But the solver programs are more popular, so I tend to spend more time on those. But look, good luck in your chemistry, your physics, your math, your SAT, all that jazz. And we got programs for you. Okay, good luck. See you next time.